We talked a little bit about longitudinal waves. So imagine you have a coil spring here. When you pull the spring outwards, the spring will start to bounce back and forth. That's what we call as longitudinal wave. Those waves, if you imagine this is the center of or the axle of the coil spring, then the motion will be parallel to the axis of the coil spring. So you can of course measure the wave length if you want to. You can see here there is some compressions and retractions. So you compress one segment of the spring and the other one will retract until the motion will be translated from one side to the other of that exact spring. Now we know what is pulse. Now how to calculate the length and speed of the pulse. And remember, the speed and length of the pulse having different equation than the length and speed for the wave. Based on the analysis of the pulse over here, you have velocity and you have distance and time. So you can say that the delta d equals v by delta t. Delta d is the displacement of the wave, and that can be replaced as the length, and that would equal the v by delta t. In this case, you measured the length from here all the way to here. That's the length of the pulse, equals the velocity of the pulse, how fast it's transferred from one side of the spring to the other, by the time, how long it took until it reached the other side of the spring. Now, it is important to keep in mind that the waves are depending a lot on the medium. A solid, such as spring, is an elastic medium and can store elastic potential energy by stretching in a longitudinal direction or in transverse direction. The way that the fluids, like liquids and gases, store elastic potential energy is by being compressed. So the waves within fluid are typically longitudinal waves, known as pressure waves. This principle used in engines and in the sprays. As the compression and retraction move through the fluid, the motion of the molecule in the fluid is similar to the motion of the coil when the longitudinal wave moves through a spring. For water to transmit energy as transverse wave, the wave must be displaced vertically, but in liquids, the vertical displacement cannot be a form of elastic potential energy. Thus, the transverse wave can be transmitted only in the surface of water in or other liquids, where the waves are the result of gravitational potential energy rather than the elastic potential energy. Now let's take an example. To create a pulse in a fixed ideal spring, you move your hand sideways in a distance of 45 centimeters from the equilibrium position. It takes 0.8 seconds from the time you begin to move your hand until it returns the spring to its equilibrium position. If the pulse moves at a speed of 2.5 meters per second, calculate the length of the pulse and describe the incident pulse and reflected pulse that pass through the midpoint of the spring. What's given? We have A as 45 centimeters. Of course, for unit wise, we need to have it as meters, so that's 0.45 meters. Delta T is 0.8 seconds, and the velocity is 2.5 meters per second. Find the length of the pulse. So we're talking here about pulses, not about waves. So the law for the pulse, we already know it. Length equals V by delta T. We have the V as 2.5. Delta T is 0.8. That would give you the length of 2 meters. For the branch B, describe the incident pulse passing the midpoint of the spring. The spring is defined as an ideal spring, so the amplitude of the pulse is constant. The amplitude at all points on the spring will be the same, and we already given the amplitude of 0.45 meters, so the answer is 0.45 meters. And the length would be 2 meters, and the speed is 2.5 meters per second at that moment. The third branch describes the reflected pulse passing the midpoint of the spring. The reflection inverts the pulse, but does not change any of the properties. The reflected pulse is identical to the incident pulse or the initial pulse, except that it would be inverted, as we learned, relative to the incident pulse. It is important to keep in mind that the waves are a form of simple harmonic motion. When you do a pulse, so the path of your hand going upwards, you create a pulse. The pulse will be going negative and positive, transferring through the spring, and you have the equilibrium position of the spring, and the direction of the pulse motion would be going to the right hand side to the fixed side of the spring. So the simple harmonic motion generates a wave train in the form of a sine curve. For a transverse wave in specific, each segment of the medium simply oscillates in simple harmonic motion about its equilibrium position in the direction perpendicular to the direction of the wave motion. So the simple harmonic motion is transferred sequentially from one segment of the medium to the next to produce the motion of a continuous wave.